Howdy! This lecture video is a special lecture video specifically dedicated to using Desmos in this course. Starting with the Unit 2 test onwards, you will be able to use any calculator of your choice in this course. If you have your own calculator, your own handheld calculator that you prefer to use, then you are welcome to use that. However, a theme of this course is not making you spend any more money than you're already having to spend on tuition, fees, room and board, dining, and other associated expenses. My hope is that you don't have to spend any money on this course whatsoever. And so therefore, for those of you that do not have your own fancy handheld calculator, we have Desmos. And starting with the Unit 2 test onwards, you'll be able to open a new tab during the test to access Desmos. As you can see, the link is in the top of the browser. It's desmos.com/calculator. And if you forget the link, you can just quickly Google it and pull it up during the test. That'll be okay. Now, of course, if you try to run around and Google some answers, that's a different story, but that would be seen. But if you're just simply using it to pull up Desmos, you'll be good to go. Now, if you're an online student in the D01 section, then you can treat this like any other lecture video. This video will be time-stamped, so that way you can easily reference which part you need help on when using Desmos for the test. For those of you in the in-person section, technically speaking, there's not a Desmos lecture dedicated to just Desmos. Rather, I show you how to use Desmos when we encounter it for a given problem. So for the in-person students, this is not an official lecture so much as it is an agglomeration of when we use Desmos. So like the online students, you can easily access when you need help for a particular problem. These are all time-stamped. They should show up as automatic chapters on the YouTube video play bar. So if you hover over it, it should clearly label which it is. If for some reason that's not there, you can just check the description of the video and it will show those timestamps as well. For each of these, I have brought over a problem from one of the whiteboards and showed the steps. I'm going to explain them step by step, describe a few extensions, and then also elaborate on some common mistakes that students will make when they enter these numbers, letters, and equations into Desmos. So, with all of that out of the way, let us begin. First up is the binomial distribution. This is in Unit 2, associated with the chapters 4 through 6, Lecture C, Video, and Whiteboard. So, in the example brought up, we have a 10-question multiple choice quiz, and you're going to be guessing on all 10 questions. What is the probability of getting exactly 6 out of 10 of the questions correct, assuming we have 4 answer choices each? In this case, the first line will always have the question replicate over. It'll be mostly italicized. Sometimes you'll see some weird hyphens or signs or whatnot. It's just a way of replicating them over for easy convenience for your viewing. So, in order to solve this, we'll use what's called the binomial distribution. As an important note for all of these, if you're not sure what, say, the binomial distribution is, or for the next one, what the Poisson distribution is, or what a linear regression is, or whatnot, I would strongly recommend that you watch those portions of the lectures before coming to the Desmos assistance video. All parts of this will assume that you're sufficiently familiar with the distribution or formula being discussed. So, on our second line, I have the binomial distribution formula typed out. When you're working with the binomial distribution, whether it's for the WebWorks or for the test, I would strongly recommend that you have it typed out exactly as we have here. So on this left-hand side, we have capital B of x, which stands for the binomial distribution given some x input. And this is in function notation. You'll see this is going to be very common when using Desmos, that we use function notation, so we can pass in our variables as inputs without having to type the formula again over and over and over and over and over until all of our fingers have fallen off our hands because they're tired of typing everything. So this formula is exactly as it appears on the whiteboard, and if you do take notes, in your notes. So once you type out this full formula, what's going to happen is right below it, you will receive prompts to add n and p as inputs. If you don't see those sliders, you can put n equals, and in this case 10. And then you can put p equals, in this case 0.25. You might say, why are we putting n equals or p equals, and where did this 10 or 0.25 come from? Well, because we have a 10 question quiz where we're guessing on all 10, we have a total sample size of 10. And because we have 4 answer choices each where you're just randomly guessing on all 10, you have a 1 out of 4 chance of guessing correctly, hence 25%. 0.25, 1 out of 4. So by putting n equals 10 and p equals 0.25, this b of x will automatically update these values in the formula for you so that you don't have to. What it also means is if you're now working with a new problem, all you have to do is change your values of n and p. You can leave the b of x completely unchanged. This will save you a lot of time on web work and will allow you to focus particularly on the problems themselves for the test. So once we've passed it our parameters, which are n, the sample size, and p, the probability of success, we can now get our answer. So b of 6 is the binomial probability of getting exactly 6 successes, so 6 correct, given we have a sample size of 10 and a probability of 25%. So all you have to do is take this 6 and just literally put b of 6. It will do this whole computation for you and give you your answer. If you're one of those old school people that likes to do the whole thing out manually, what you would do is you would put n factorial, so 10 factorial, over your input x factorial times 10 minus 6 factorial times p, which is 0.25, to the power of x, which is 6, times 1 minus p, 0.25, to the power of n, which is 10 minus x of 6, and you'll notice we get the same answer. However, I think we could all agree it is much easier and much less clumsy to do it this way. Furthermore, suppose I also asked you for the probability of getting 7 correct. Well, if you wanted to do this with 7, you're going to have to take this whole thing and switch all of those 6s for 7s. Alternatively, we can just put b of 7, and that's it. So you can see how using this notation in lines 2, 3, and 4 makes it much easier for you to do the work. I'm going to show you a very clear example for why doing this is better than this. And I am about to delete this line. If you wanted to have this line up for another moment, you can certainly always pause to ensure that you're caught up and good to go. And if at any point you find yourself a bit confused, you can always just rewind and go over that part again. So now let's suppose I reworded the question. Suppose you want to get an A. So suppose you want to randomly guess your way to a 90 or higher. In this case, 90%. What is the chance of that occurring? In this case, a 90 or higher would be either a 9 out of 10 or a 10 out of 10. So 9 out of 10 or the 10 out of 10. What? And here we go. I don't know what this is doing. There we go. 10 out of 10. So in this case, all we have to do is put b of 9, which is the probability of getting 9 out of 10 correct, plus b of 10. 10 out of 10 correct. As you can see, that's very small. You're not going to guess your way to an A unless you're extremely lucky, and you're definitely not going to guess your way to an A in a course if you're guessing on every single question every single time. Maybe once a millennium, you might find somebody getting that lucky, but as a practical matter, as you can see, that's a bit crazy. And so therefore, the best use of this binomial formula with Desmos is that when you're getting cumulative probabilities, say 9 out of 10 or higher, or say 3 out of 10 or lower, it's as easy as that. Finally, for the binomial distribution, let's go over some common errors, specifically when typing in this formula. There are two major mistakes that students make. So I'm going to copy and paste this so you can see those two mistakes. The first one comes when students are typing in this part to the right of the x factorial. They'll put their parentheses, they'll put n minus x, but they'll forget to put the n parentheses and will instead put the factorial first. See the problem? Our factorial is now on the x instead of on the parentheses. Off to the right, you can see this red line is what the binomial distribution is supposed to look like. You can see this blue line, if you could even call that a line, is what happens when you put the factorial in the wrong spot. So that's the first mistake. So if you get some weird, goofy result, double check that your factorial is on the outside. The second mistake that students will make is when they are putting this n minus x in the exponent. So when they do that, they'll do the caret symbol to put it in the exponent, and they'll just literally type in, without parentheses, n minus x. If you do that, what will happen is the minus in the x will be dragged back down to the rest of the equation, and now you just have a line. So in this case, that's why up here I have it in parentheses. So what you can do is first put the parentheses and then put n minus x, so you can avoid that problem. Finally, you might ask, hold on a moment, how did you even get this exponent? How do I get an exponent in Desmos? So on your keyboard, on the 6, if you hold down Shift and then press the 6 on your keyboard, not the numpad, on the top of the, like above the letters, you can then get the caret. So to put it here, you're going to hit Shift and 6. And so Shift 6 will give you that exponent. So if I have 5, I'm going to do 5 to the power of 5. Shift 6 puts it up there. So that is how you get the exponent. That is the binomial example. Let's move on. Next up, we have the Poisson distribution. You might say, the Poisson distribution sure looks like the word poison. Here's the thing you need to realize. This is named after a French guy, and the French are very good at 3 things: pastries, naming things after themselves, and losing wars in half a second. In this case, because they like to name things after themselves and pronounce their names in extravagant ways, we have the Poisson distribution. So in this example, we have a CVS pharmacy drive-up teller where we have arrivals and non-arrivals of people being independent of each other with an average of 5 cars per hour. What is the probability of exactly 4 cars arriving? This is from the chapters 4 through 6, lecture B, whiteboard and lecture video. In this case, we will usually use the Greek letter rho. And it's not spelled R-W-O, but technically R-H-O. And so you can get your P like that. On the other hand, you can just use a capital P here. That's fine as well. If you wanted to switch it to rho like that, you're good to go. Either or is fine. So here, I use the letter M to denote the mean, but you can also use the Greek letter mu, M-U, to denote it, but as you can see, it's technically another letter and it might get a bit confused, so you can just say M for mean. So for the Poisson distribution, and by the way, the subtitles are going to have absolutely no idea what to do there. It's poison with another S in there. So here we have m to the power of x, where m is our mean. We have e to the power of negative m, and we divide the whole thing by x factorial. The only input you have to pass is the m, which in this case our mean is 5 because we have 5 cars per hour. You might ask, why don't I have to pass the letter e? Well, e is Euler's number, and it is 2.71828 blah 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 blah. Desmos takes care of all those decimals for you. all you have to do is put the letter E. You might say, hold on a moment. We had rho for Poisson, with the Greek letter rho looking like a P. How exactly do we go from Euler to E? Because you might think Euler starts with an O. No. See, this is a French guy, which means we spell it that way. I didn't make up the pronunciations. I just say the words. Take it up with the French people. Regardless, you can just put that E and it will take care of it. So all you have to do is just pass the input of m equals 5. So, at that point, we're ready to go. Just like with the binomial distribution, we're ready to go. And the good news is, unlike the binomial distribution, it is very rare for people to make an entry mistake up here, because the negative with the m takes care of it immediately, since you don't have, say, an n minus m. So now that we have that, if we're looking for the probability of exactly 4 cars arriving, all we have to do is put Poisson of 4, and we get that probability of 0.175. That's it. Nothing else to it. Poisson is considerably easier in terms of entry than the binomial distribution. Now, if you wanted to enter this manually, you could put, in this case, 5 to the power of 4 times e to the power of negative 5 over 4 factorial, and you see we get the same answer. Like with the binomial distribution, though, the particular value of doing it this way is when you have to do cumulative probabilities. So, for example, suppose I ask for the probability of no more than 1 car arriving. In this case, that's going to be equal to the Poisson of no cars arriving plus the Poisson of 1 car arriving. As you can see, that probability is not great. So if you were looking to help out a customer and then go to the bathroom, it's not going to be easy. You're probably going to want to have another worker there to take your spot while you do that. So that's the Poisson distribution, considerably easier than the binomial distribution, and these two are the ones that would constitute the help you would need for the Unit 2 test. So now, let's move on to Unit 3. Sample sizes. This is from the Chapter 8 lecture video and whiteboard. You might see it stated as Chapter 8A and 8B. This is because for the in-person students, we split up the Chapter 8 lecture, since it would otherwise mean that one lecture would go quite far past the cutoff time. And I'm not interested in holding people until 4 a.m. in the morning. So they have it split up, but it's technically not quite long enough to warrant putting it as 2 separate lecture videos, so they're technically combined with their time stamps. So let's suppose we have a population standard deviation of 55. Let's estimate with a margin of error of 12 the needed sample size for 90% confidence. Here's how you want to do these. Define your margin of error E to be, in this case, 12. Your population standard deviation is 55. Technically speaking, this is going to be the lowercase Greek sigma. Here you can just P of stdev, and you're fine. As you'll see in the formula here, I just go to the numbers directly, but I'm technically defining them up here for those of you that like to see your numbers defined. You finally need your critical value. The critical value is 1.645 and comes from the Z confidence tables, which I have here. Since we have 90% confidence, we have an area of 10% in each tail. 10% in both tails, and so 5% in each tail, meaning we have a Z of alpha over 2 of 1.645. If you're not sure where that came from, then you should double check those timestamps for the Unit 3 lecture videos. So you might say, well, this seems straightforward. Why the hell are we using Desmos for this? Simple, because for sample sizes, you have to round everything up. Even if your final answer is 56.001, you have to round that up to 57. You might ask, why? 2 reasons. Number 1, how exactly do we sample 1% of a person? That doesn't make any sense. How exactly are we going to have half of a car? I suppose if you drink a lot of Jack Daniels and plow your car into the side of an underpass, then sure, you might have half a car, but for all intents and purposes, half a car is not a car. And we can go on and on, but the underlying point is with sample sizes, we have to make them integers. Here's what happens if we round down. If we round down, then what's going to happen is, as you can see with the margin of error formula, that's going to actually include more uncertainty than we're trying to include. So by rounding up the sample size, we account for that uncertainty. So always round up. And this is why I introduced Desmos here. Desmos has something called the ceiling function, spelled C-E-I-L. If you quite literally type that in and then put your parentheses, it will round everything up for you. And that's what it's done here. So all we have to do is pass in our inputs of 1.645, we square that, 55, square that, and divide that by 12 squared. If you took this and you brought it out on its own, we'd have an answer of 56.845. So at this point, you might ask two questions. Number one, well, it's rounding up to 57 anyways, so why couldn't we just say, put round? Because that works. The reason why we can't do that is what happens if we have a different population standard deviation. What if it's 54.7? In that case, we're going to be rounding down. So this is why you don't use the round function, because it might round down for you. The second reason why is some students will forget about the rounding at all. And they'll say, haha, my answer is 56.845. I'm going to put that into WebWork. And WebWork's going to come back and say no, because you have to round it. Even if your final answer is like that. Or like that. See how close you are. You're off by maybe 0.01. Even though it's off by a small amount, it still doesn't make sense to have 98.8% of a car. We might colloquially think, well, you're just forgetting a pipe, who cares? But in terms of sample sizes, you have a car or you don't. You have a person or you don't. You have a bird or you don't. We can go on and on. That's why we don't use the round function. And the reason why we use a ceil function is it will round this up for you so you don't forget about the integer rule. So by using the ceiling function, it not only takes care of the rounding for you, it also takes care of the integer rule. So that is using Desmos for the Unit 3 test with the new function. Again, C-E-I-L. So finally, let's move on to the one where Desmos is perhaps most useful. Linear regressions. So from the Chapter 13 lecture and whiteboard, I have reproduced the 5 coordinate pairs. And we're going to compute a linear regression of these. On the test itself, you'll get to use the shortcut method. The shortcut method is detailed in the Chapter 13 lecture video. You'll want to make sure that you have that understood and written down for use on the test. Most of the time, you'll have a computer do these things for you. Here I'm showing you that process, and you'll need to use this process on a couple of WebWork problems. So the first thing you want to do is define your x mean and your y mean. So the sample mean for the x values and the sample mean for the y values. So we have xm, and this is quite literally just the mean formula from Unit 1. Same idea for the y values. Now at this point you might say, hold up, how in the Lord's name did you get that subscript? How did you put the m down there? The way we do that is with the underscore. The underscore comes from using the shift key on the minus sign in between the 0 and the equal sign on the main keyboard. So you have your 9, your 0, then you have the minus, and your equal sign. So you take the shift of the minus sign. So if I do shift plus minus, it'll give you your underscores. For example, if I have y, shift minus, we now have our underscore. So you'll put shift and the minus sign. That doesn't mean shift and then literally the plus sign, that just means what you combine. So again, shift, oh, what did I just do? Oh, that's fine. shift and the minus sign. That's how you do it. Again, not the minus sign from the numpad. The minus sign to the right of the 0 on the main keyboard. So now we have our x mean and our y mean. Let's continue. We're going to define a function f of x, y with our input x and y, quite literally inputting the coordinate pair. And we're going to have it be x minus the x mean times y minus the y mean. This constitutes part of the numerator for computing b1. Likewise, we'll do the same thing with g of x, because our denominator has the squares of the differences for the x values, just like the numerator did for standard deviations. This time, we just have to input the x values. Once we have these two, we can move on. So t stands for top, i.e. the numerator. And this is going to be equal to f of each input. So f of -1, 0, the first coordinate pair, plus f of 0, 9, the second coordinate pair. And we keep going until we have all of them. You could literally do this step by step for each one, but your fingers will be dead. You'll have a $400 electricity bill, and I don't think that's something we're especially interested in. Am I exaggerating a little bit? Yeah, but the point still stands. If you're wondering why this is the numerator, then you should refer to the Chapter 13 lecture video where the least squares regression is explained in theory and concept. And then likewise, b stands for bottom, the denominator. And this is equal to the g's of our x values. Do not put the y values here. It's just the x values. So -1, 0, 4, 7, and 11. That gives us the value for our denominator. So now that we have the value for our numerator, 178.8, and our denominator, 98.8, we divide the top by the bottom to get b1, which is 1.809716, blah, 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 blah. And then finally for our b naught, or technically b0, and naught doesn't mean N-O-T, it's N-A-U-G-H-T. Again, this time it's the Greeks, why not? We have our y mean minus the computed b1 times the x mean. And this gives the b naught of roughly 5.599. And thus we have our regression equation of y equals b naught plus b1 times x. And there you can see it on the red line. And now you can do some regression. So for example, if you want to do y of x, technically speaking, you could get the predicted value for -1. And so in this case, technically speaking, I'll put f of x, or I already have an f. Let's put h of x. So if you give it an input of 1, it's going to predict a value of 7.4. If you give it a value of 0, it'll predict 5.599. So that's how you do the linear regression with Desmos. Those constitute the main examples of using Desmos for the tests. I hope you found this agglomeration to be helpful. If at any point you're a little bit confused on the concept, then you should watch the corresponding part in the lecture videos, which are time-stamped, and I referenced those lecture videos earlier in this video as we approach them. And then once you have those concepts understood, you can always come back to these. I recommend that for each of these problems, you try them yourself to ensure that you have those inputs correct. So with that said, that constitutes the Desmos lecture video, Desmos assistance video, or whatever you'd like to call it. Have a great rest of your day.